So what I'll do is I'll just get started. So once again, if anybody has any trouble with the audio, feel free to just type into the chat box and let me know. All right, so once again, today's session will be on time history and response spectrum analysis for a bridge abutment. And for those of you who may need to contact me at some later point, here's my contact information. Okay, so first let's just discuss the session objectives. So first, we will provide a review of the fundamental concepts of response spectrum and time history analysis. So I understand that a couple of you are still somewhat new to this, or new to seismic analysis in general. So what I'll be doing is just going over general concepts so that you understand just the basic gist of response spectrum and time history analysis, as well as seismic design in general. And then the focus of the demonstration, or today's session anyway, will be how to create a numerical modeling program, or excuse me, how to create a numerical modeling simulation of both of a time history and a response spectrum model using a bridge abutment. So first, this will be just a general introduction, and this will be sort of the heart of today's lecture, is the demonstration itself. So for those of you who are users of SoilWorks, this should be particularly useful to you. So let's go over the course contents very quickly. So first, I'll give you a review of response spectrum analysis, followed by a review of time history analysis. And then I'll just very briefly go over the scope of the demonstration. So this is very important because I understand that we have some users here, some engineers who are still new to finite element modeling. So it's very important to understand, the scope of the demonstration, what's involved, and also sort of the process for numerical modeling, because finite element analysis does follow a very sort of set process, and it's very important to hit all of those steps. And then last, we'll give the demonstration itself. So first, I'll give just an introduction to what we're doing, and then I'll actually put it into practice. All right, so first let's discuss response spectrum analysis very quickly. So response spectrum analysis is required by many building codes, and it's used for everything except for very simple or very complex structures. So very simple structures would include, one-story buildings or very small sort of warehouses. Those typically used a different sort of, or a very sort of simplified seismic analysis method. And complex structures include, very large warehouses, high-rise buildings, very large-scale type projects. So, response spectrum analysis is the most widely used form of seismic analysis, just because it sort of hits that middle ground. So it's the most sort of conventional analysis type used. And it's useful when detailed time history records are not available. So I'll talk more about what time history records are in the next section. But just keep in mind that response spectrum analysis is used for sort of middle of the road projects where you don't need a very high level of analysis or a high level of detail in your analysis. And it utilizes multiple modes of response for a structure. So some of you are probably wondering what these pictures represent. So when you're doing a response spectrum analysis, essentially what you'll have is several sort of modes that you'll be studying. So for example, each of these pictures here below represents a different sort of period of the wave. So for example, let's say the earthquake just starts, and this is sort of what the vibration looks like, and this would be the mode associated with it. However, when the earthquake picks up, for example, the frequency or the intensity and the strength of it might increase, and then you would have a different sort of modal shape. So here, you just have one mode to represent this one sort of deformation. But here you would have, I believe, two nodes, to represent this type of deformation. And then, finally, maybe you have like a critical stage where the earthquake is at its strongest, at its fastest, and then you'd have something such as this. So you'd have maybe up to 3 or 4 nodes. So just keep in mind that depending on where you're at with the earthquake, your structure could be under a different type of loading. So for those of you who are very familiar with seismic analysis, you'll know that when a building or any type of structure is subject to seismic loading, the way that the loads are oriented really sort of starts to shift. Just think about a load sort of acting back and forth, along the base of the structure. So depending on sort of where you are as far as the strength or the intensity of that earthquake, you'll have a very different reaction from your structure because the loads will be acting on it very differently. So that's the whole sort of concept behind doing different mode shapes. So that's just something that you should be familiar with if you're familiar with response spectrum analysis. So that's something that's very important to understand when obviously when you're creating a numerical model as well. Okay, so yeah, as I explained, it assumes a responsive multi-degree of freedom system for a combination of multiple single degree of freedom systems. Okay, so now let's move on to time history analysis. So the main sort of principles or the main concepts to understand about time history analysis is that it's performed when a detailed evaluation is required or when complex structures and ground conditions exist. So it takes more variables into account, it requires more time and effort to perform, and it requires the use of time history graphs or past earthquakes in the area. So time history analysis is really used for larger scale projects, projects in high seismic regions where seismic analysis or seismic design becomes more and more prevalent. So the main advantage of time history analysis is, like it says, it takes more variables into account, so you can get something that's much more accurate, and you can get designs that are much more optimized through time history analysis because you're taking sort of more time to make a more thorough type of analysis. The drawback, though, is that it requires more time and effort to perform. So that's one of the main things that engineers need to consider when they're deciding between response spectrum and time history analysis is will it be worth the investment? Like, is this a project that would need this sort of level of detail? So typically companies that work out in sort of seismic regions or projects that are located in high seismic regions or in California typically use time history analysis very regularly, whereas companies that are out in the East Coast or the Midwest, response spectrum analysis is the most prevalent. And then the data for time history records or time history graphs, they apply to various step functions listed here below. But essentially what time history graphs and time history records are, it's a sort of a list of sort of notable earthquakes in a particular area. So for example, let's say you have a project in a high seismic region such as Los Angeles. Then you would have sort of a list or a database of sort of large, very eventful earthquakes in the history of that area. And you would use these time history records to design your building or to sort of simulate sort of the critical conditions or critical earthquakes on your building. And we'll discuss that in a little bit more detail coming up. So going on, so something that's very unique about seismic analysis in general is the use of soil springs. And forcing functions as well. So here we have an example of a driven shaft pile or a drilled shaft, and here we have several soil springs acting or modeled on these nodes. So essentially what a soil spring does is it simulates sort of the damping or the vibration acting on your structure. So for example, if you subject this pile to a seismic loading, it's going to oscillate, and depending on the type of soil it's pressed up against, those oscillations sort of vary, which it relates directly to something called the damping ratio. So the higher the damping ratio is, the more stiff or the more solid your soil is, and the more it resists seismic loading. But the lower your damping ratio is, the more weak it is, and the more susceptible it is to failure and towards
high oscillations.
So just keep in mind that each of these soil springs, what they do is they simulate those oscillations. So just think of it as like a bed spring. So if you were to sort of put a certain amount of force on these bed springs, or on a bed spring, you would oscillate back and forth. So that's essentially what's being done with these elements here. And I'll show you how to create these elements or how to define these elements in the demonstration coming up. So the soil springs are defined along the length of your structure, and depending upon which sort of soil layer it's pressed up against or it's in contact with, the properties of the springs will differ. So beforehand, typically what engineers do is they'll have their damping ratios, or excuse me, their damping coefficients created for each of their soil layers. That way they can just assign them to their springs when they're doing their modeling. Okay, and as far as time history analysis, essentially in order to get your time history records, you just have to get your time history data, and it's typically, the database is available to you. They're usually, a matter of public record. So, I'll just sort of I'll breeze through this part here because essentially, what I want to tell you is just that, time history records, they're found by, they're developed by scientists who have studied certain seismic regions over a long period of time, so that engineers, when they're doing the designs for their buildings, or excuse me, the seismic designs for their projects, they'll have these records available to them, and they're based on various sort of specifications. Okay, and once again, something that's really important to understand is that it's really up to the engineer to decide which sort of time history graphs to use, which data to sort of filter and use in their project. And really it depends on the project location, the scope of the project, on several variables. But the main idea is that these records are available to engineers when they have these types of projects. Okay, so before we move on, let's just have a quick comparison between time history and response spectrum analysis. So the main pros of time history analysis: in some cases, it's possible to have a reduction in steel reinforcements and possibly concrete. So essentially what engineers use time history analysis for is to get really optimized results. our optimized design. So in areas where there's a lot of seismic activity, usually the company that has the most sort of realistic yet also economic bid will get the project. So time history analysis is used extensively to get optimized designs in high seismic regions. Once again, you can lead to cost savings, reduce substructure quantities. So there are many ways to go about using time history analysis to get really sort of optimal designs. And then the cons of time history analysis. First, it's not applicable or it's insignificant for conventional type projects. So for those of you who are working in sort of low seismic regions, very rarely will you ever need to use time history analysis, if at all. So for the most part, you'll be sticking to response spectrum analysis because, it's not as optimal, but it requires much less effort and it's adequate for most conventional projects. And then time history analysis is very time consuming and requires significant computing. So once again, it's a larger time investment. But that's really up to the engineers or the people in charge of the project to decide whether or not it's something worth investing in. But these are just important things to know about the two analysis types before really starting to use them. Okay, so first, now let's move on to the scope of our demonstration. So this is what our project will look like once it's completed. So we have 4 soil layers, or excuse me, 2 rock layers and a soft rock layer on the bottom with the landfill layer on top. Here's our abutment, and then our piles will be modeled as well. So this will all be done in 2D. Okay, so I won't spend too much time on this, but this is just our ground material properties, and it's all based on the Moore-Coulomb model and the elastic ground model for the abutment. So just make sure to have these sort of material properties available to you and on hand before you start your project. Okay, and then the scope of the demonstration. So here is how the demonstration will proceed. So first we'll do the modeling. We'll import our AutoCAD file. So for those of you who use SolidWorks, I'm sure you understand how to use the AutoCAD import function. And then we'll define the material and structural properties. Then we'll create the surfacing, which is very important. So I understand that several of you are very new to the program or still looking into the program. So this is a very key step, which I'll explain in detail. And then we'll assign the material and structural properties to the surfaces and the lines that we've defined previously. We'll assign the boundary elements, or in this case, the surface springs, because this is a seismic design project. And then we'll generate our ground accelerations using actually a database that's available to us in the program itself. So I explained how all of these sort of time history records are available to you. They're sort of a matter of public record. Something really unique and powerful about SolidWorks is that all the records are available within the program itself, so you don't have to actually look into any outside sources. And then defining the analysis cases. So once again, another key a key advantage of SolidWorks is that you have the opportunity to create multiple analysis cases within a single file. So this is particularly useful if you're running different analysis types on the same project, or if you're doing a design project where you want to try multiple sort of scenarios and you want to compare and contrast your results. So once again, I'll go into greater detail about creating analysis cases near the end of the demonstration. We'll run the analysis. So because the analysis could take a couple of minutes, I already have a couple of pre-solved models available. But that's, obviously a very important step. And then we'll extract the results. So, because it's a finite element model we're creating, the results that we get are very sort of detailed, even though the model itself takes a very short time to run. So what I'll do is I'll just, briefly review how to find the results that are of interest to you. Okay, so that about does it for the introduction. So now let's get to the heart of today's demonstration, and I'll just open up the program here. Okay, so here is the start screen of SolidWorks, and just keep in mind that we're in the dynamic module. So as you can see here, it says dynamic analysis module. So when you're opening up the program, just click on this icon here. It looks sort of like a vibration wave that represents the dynamic module. And then what I'll do is I'll just get started with creating our basic model, and then I'll go over the sort of key differences about the dynamic module and what makes it very special and very unique. So yeah, for those of you who are still new to the program, let me just quickly give an overview. So let's say, for example, if you don't have an AutoCAD drawing available to import directly, what you can do is you can just use these CAD-based designs to do the drawing for you, or to create the drawing. So if you're familiar with AutoCAD, all of these functions should be very familiar. Also, you can type in commands in the command bar if you want to draw lines, circles, etc. It accepts all of those commands. So I already have an AutoCAD file prepared for me. So what I'll do is just go to the SolidWorks icon, go to Import, and then just select a CAD file. So here I have my CAD file ready. So when you have the one selected that you need, just double click, and then just give it a second, and then the drawing should be imported. Okay, so here we go. So as you can see, everything is imported just directly into the program. It's very convenient. It's very easy. I had a couple of questions in the past about how to change the scaling. So for example, I believe someone had a project that was drawn in AutoCAD, but the scaling was off when it was imported. If you want to change the scaling of your drawing, just go to Geometry, and then just go to Scale, this option here. And what you can do is you can just click on it. You would just have to select your project, or excuse me, select your objects, and then it'll ask you, just press enter here, it'll ask you for your base point, so let's say here, and then it'll ask you for the reference. So as you can see, I can scale my project accordingly. I can, this is just sort of eyeballing it, but if I want something more definite, I could just type in a factor of here. So if I want everything increased by a factor of 2, just type in 2 here and press enter, and then everything will be doubled in size. Or if you want to decrease it, say by half, just type in 0.5 and everything will be decreased by half in size. So that would be how you would use the scaling option. Okay, so now going back to just our modeling here. So everything here is to scale, so I don't need to change anything as far as that's concerned. But now I need to create my material properties. So in order to do that, go to Model, and then go to Ground Material Property. So open up this tab here, and as you can see, I already have the abutment just sort of pre-made. It's under the Elastic Ground module. And for those of you who are still sort of new to the program, who are looking into it, if I open up this model type here, or if I open up this, this drop-down menu, here I have the 3 main model types that are available to me in for seismic analysis: elastic ground equivalent linear, and then Moore Coulomb. So all very simple and very straightforward constitutive models. So what I could do is I could create my own sort of material properties by entering in entering the properties individually. Say you have a spreadsheet of the material properties that you're working with. You just have to go down this list here and make sure everything's entered correctly. And then also, naturally have to make sure your units are correct. And you can change those by clicking on these 2 drop-down menus here. And also keep in mind, if you need to change your material properties after you've already entered, say these are in the correct material, or say these are in the correct units, but you want to change the material properties, or not the material properties, the units later, you can just change them by using these drop-down menus. So you don't have to sort of go back and change everything. But in any case, just to speed things up, what I can do is I can go to my database here, and this is a very sort of key function that a lot of clients have made a really good use of, just this database. So just click on this database here to the bottom left, and as you can see, if I go to this drop-down menu, I have a list of all these different material properties saved for me. So this saves me a lot of time for example, let's say I have multiple projects in the same region. I'm using the same sort of material properties. What I can do is I can save them in this database, and then I can just save them for future reference. So later on, if I have a similar project and I want to use those material properties again, I can just call them up through here. So let's go to, and as you can see, this whole sort of bottom half here is specifically for dynamic characteristics or for seismic analysis. So for those of you who are using SolidWorks for dynamic analysis for the first time, it's really worth it to look into these material properties and just to see if there's maybe, sort of a list that, matches up with the types of materials you're currently using. That could, save you a lot of time in the long run, definitely. So let's go to this one here, or actually, let's go to schist. There we go. Okay, and then let's say, for example, these are close but not quite exactly what you're looking for in material properties. You can actually change these yourself, so these can be user-defined, and then you can save these for future reference. So let's say, for example, you have a project in a specific location, and you want to save these material properties. Just make sure to change them according to your needs, and then click Save. That way, when you have another project in that area, all your material properties are ready for you. So let's say I want to select, I think we had an alluvial layer. Or actually, no, we had a landfill layer, sorry about that. And then we had a weathered soil layer, or excuse me, we had a weathered rock layer and a soft rock layer, and I think it was a weathered soil layer. So yeah, let's just choose these 3 now, and we'll click Assign. Now as you can see, we have, our material properties are now ready for us, along with all of their corresponding parameters. So that's just a way that you can save a lot of time in the long run, because I know it can be sort of tedious to type in material properties individually. Maybe sometimes if you have something lengthy like this, you might miss a decimal point or something. So that's just something that could save you a lot of time in the long run. It's just having your material properties saved and ready for you. So now I have these created. I can click close. And if I go to the left here, if I go to this work window, as you can see, everything that I have defined is saved under these drop-down menus. So that way I can just refer to them very easily. So right now these are in blue, which means they haven't been assigned to my model yet. Later on when I assign these, you'll see how these change from blue to black. So this is just a good way to alert you of like certain parameters or properties that are currently not active in the model. So now that I have my material properties, my material properties for my soil layers, I also need structural properties for these abutments, or these piles here. So if I go to Model, Structural Property, as you can see, in the interest of time, I already created my pile, and these are the parameters. Here's the diameter, and the stiffness calculation is automatic. And then the material data, I believe I think it's a user-defined material property, but I can change it to concrete or steel, depending. There's preset parameters, but these can be user-defined as well. And then for those of you who are wondering what other sort of shapes are available to you, everything from rectangles, pipes, boxes, etc. These can all be user-defined. So any sort of pile type shape or structural reinforcement shape you might need are available to you just within the program itself. It's just a matter of sort of going through the drop-down menus to find the right one. Okay, so that's how you define your structural properties. And then if I go to my structural property drop-down menu here, I have my pile. It's a beam type element. It's not in use yet. And then just keep in mind that my abutment, I gave it, it's concrete, so I just gave it concrete properties. And what I'll be doing is I'll be assigning it to this enclosed area. But in order to get a better understanding of that, first we need to do our surfacing. So I know that maybe some of you who haven't had much experience with finite element modeling are wondering, why can't I just, assign a material property to this enclosed area? So the reason we have to create our surfacing, and I'll do it right now actually. So just go to Geometry and go to Smart Surface. Click on this tab here. And as you can see, the surfaces are created for you. So the reason that I need to create these smart surfaces is because currently, before I did that surfacing, the program only recognized the lines. They didn't recognize sort of an enclosed area here. So in order for me to sort of assign a material property to this particular enclosed area, I'd first need to create my surfacing. So in order to create sort of a 2D plane between these 1D elements, that's surfacing, that's how it's created. So just keep in mind that when you use a smart surface option, what happens is any enclosed area within your drawing will have a 2D surface to it. Now what you can do if you want to do it sort of manually, or to create your surfaces manually, is you can go to just go to your geometry option here, and then just create your surfacing using this option. And that would just, through this option, you would just select sort of each enclosed area by using these, or you'd select an enclosed area by selecting the line surrounding it, and you'd be able to create your surfaces individually. But the smart surface option is just the most convenient way. So let me just change the display option real quick, just so that you can get a better idea here. Okay, let me see if I can change it here. Here we go. So we'll change this to true. Okay, so the reason I did that was because currently, the program just sort of selected random colors for each enclosed area or each surface. But by changing that, and let me go back again just to give you a better view. So go to General, go to Background, and then Filling Color when selected. Change that to true. So that tells the program that when a material property is assigned to a particular surface, that surface color will change to the color that you assigned it for the material property. So if I go back here, if I go back to ground material properties, as you can see, I have a different color assigned to each of these materials. So later, when I assign these materials to to a particular area, I'll be able to see exactly, where it is. So let's change this to green to get a better idea. And let's move along with this project now. So here we have the soft rock, or the soft rock layer. So just select it by windowing it, then select this here on the select soft rock under the drop-down menu or under the work window, and then just drag and drop it. As you can see, it goes from blue to black, so it didn't change color yet. So there must be another setting I need to turn on, but just in the interest of time, let's just move along here and assign the rest of my material properties. And we'll worry about changing the display later. So this will be the weathered rock layer. Just drag and drop it. And then as you can see, once it goes from blue to black, that means it's in the material's been assigned. We'll drag and drop weathered soil, and then the landfill layer will be assigned to these areas here. So there we go. And then last, the abutment. So we'll drag and drop this here. And then last, our structural properties, we'll assign it to these 4 lines. So here, these will be our piles. So we'll just window each of these. And then we'll do the same process, just drag and drop. And as you can see, these are highlighted in yellow now just to let you know that these have these particular structural properties, and this is just sort of an estimate of how wide those piles will be. So that's essentially how you would do your assigning your material properties. So currently the colors don't match up with my material properties, so once again I have to go back to the setting. But let's say for example you just want to very quickly check to make sure that this is the correct material property. What you can do is you can window the section or the layer. You can right click and you can select object information, and then this will come up. As you can see, it'll tell you what exactly it is. So this tells you it's a landfill layer. Perfect. And let's say I want to check to make sure this is this has the abutment property. So just window it, right click, select object information, and then it's the abutment now. So that's just another way that you can make sure that your material properties are assigned correctly. So now that this is done, my next step will be to create my meshing. So just go to Model, and then go to under this Mesh tab here. You have different options or different ways that you can create your meshing. So for those of you who have extensive experience with finite element modeling, these options here look very familiar: map mesh, grid mesh. These are just essentially ways to manually create your mesh. So in other words, you'd select this option, and then using this drop-down menu, you'd have to select a surface or a set of lines. You have to define your spacing manually. So it takes a little bit longer, but it does give you more control over your meshing. But for those of you who are new to finite element modeling and who really aren't very familiar with those types of commands, it's really actually not necessary. What you can do is just use the Smart Mesh option or the Auto Mesh option. Preferably, I prefer the Smart Mesh option just because it's by far the easiest. So once again, for those of you who are very new to finite element modeling, this option is really the best one for you to get started. And maybe later on, when you get more experience, you can try the sort of the manual way of creating the mesh. But all you really need to do is select your parameters. So let's make it very fine or very sort of smaller meshing. So the program just sort of automatically recognizes where the mesh needs to be finer, so you don't have to worry about defining the spacing yourself. And then let's generate higher order elements, or higher order elements are typically used for slope stability analysis. And since we have a slope here, I think it'd be a good idea to have higher order elements assigned just in case. So what we'll do is just click OK. And as you can see, your meshing is just done automatically for you. So, once again, even for those of you who are, very experienced with finite element modeling and are used to the old way, this way still may be of, very good use to you. Let's say, for example, you don't feel like having to go step by step to create your meshing. You can just use the Smart Mesh option. You'll have a very efficient mesh set created for you within a matter of seconds. Okay. And then before I continue, I just want to give a heads up that all of the mesh sets are just listed under here, under this option here in the drop-down menu. And then each of the mesh sets is just named automatically, just according to the type of material property it's been assigned to. So as you can see, the beams, or the piles, have been meshed. I can turn them on and off. And then also the soft rock has been meshed, and it's been named soft rock. And you have multiple weathered soil layers, and each of them have been named and meshed accordingly. So these are good ways where you can sort of go back and you can check to make sure that all of your meshing is done properly, that all of the assignments are correct as far as material properties, etc. And if you want to close the menu, just click on here, and then it closes everything up for you. So once again, this work window becomes very, very important for larger scale projects where you have a lot of information and you want to double check things. It's just a matter of navigating this and to find out, which sort of set or piece that you want to investigate or look closer into. Okay, so now that we're, our main portion of the modeling is done, let's go to the dynamic characteristics. So what sets the dynamic module apart from the other modules lies in these commands here. So for those of you who are familiar with the program, I'm sure everything so far has been very straightforward, very familiar to you. But now that we're going to seismic analysis, as you can see under loads and boundary types, we have something very specific here. We have response spectrum analysis. So these two icons here are used for creating your response spectrum loads. So we'll discuss that after we do time history analysis. And then this tab here, as you can see, it's much larger just because there's more information, or excuse me, there's more icons anyway, because time history analysis is much more detailed and in-depth and requires more information. So these are the main sort of differences. This is what sort of sets these dynamic module apart, is these icons here. And before I get into that, let me just make my surface springs first. So in order to create your surface springs, just go to the right here under the element tab and then select, well, actually there's two ways you can create your surface springs. So, as I said previously at the introduction, is when you're creating surface springs for different sort of soil layers, each one will require sort of a different sort of function. So let me open up this real quick. And as you can see, what I can do, let's say for example, I want to create a set of springs for the landfill layer here. I'll just put in, let's type in landfill. And then the element width, let's make it 3.281, so roughly 1 meter. And then so element boundary curve, and then damping constant. So here you just have to define your damping constant. So I don't have the equation offhand, but just using the material parameters that are available to you now, or the ones that came with a more Coulomb model anyway, Poisson's ratio, modulus elasticity, and a couple of other ones, you'd be able to define your damping constant for each of these layers here. So let's say, for example, let's just put in some default values here, 3, 4. These aren't right, obviously, but I'm just for the sake of argument, let's say that's what they are. And then I would just select this this portion here. I would click apply, and then a series of springs with these damping constants would be applied for this layer. And then I'd have to do the same thing for my soft rock layer and my weathered soil layer, etc. And for my second layer, obviously I have to select this side and this side because these are parts of the boundaries, which takes a little bit of time, but which is very doable if you prefer to do it manually. But then also what I can do, so if I go to model and if I go to auto generate boundary element, this just automatically generates my boundaries or my surface springs for me. So what it does, it takes your material properties into account and creates springs for each of these layers, which can save you a lot of time in the long run. So let's just do that. Okay. So what we'll do is we'll name this springs, or we'll just name this boundary set. Yeah. So let's make sure to select the viscous boundary, just because once again these boundaries are viscous, so they move. This is a seismic analysis. And then make sure to select all of the mesh sets. So in order to do that, what you can do is click in the model window and hit Control A. As you can see, all of the mesh sets are just selected automatically. And then just click OK. And as you can see, within a couple of seconds, all of your soil springs are created for you, which is and as you can see, there are structural properties too, or they have structural properties. So as you can see, each of these springs here, it's sort of hard to see, but each of these corresponds to one of these springs. So once again, that's another great feature about the program, is that it takes these steps that are sort of longer and repetitive, and it has special functions to cut down on the time it takes to do them. So obviously before you use these shortcuts, it's really important to understand what's going on when that happens, so that way you don't make any sort of simple mistakes that would change the or that would give you inaccurate results. But once you have an understanding of those concepts, or an understanding of surface springs and what's going on, it's just a matter of making sure you have the right material properties. Then you'll be able to, use a function such as the one I just used to really breeze through sort of longer, repetitive steps that, in other programs or, through spreadsheets takes much longer to do. So once again, that's just a really great sort of a function of the program, is that, it's really geared towards helping engineers work more efficiently by cutting out really long, repetitive steps that previously, used to take up a lot of time, that used to be, somewhat wasteful for engineers that are very familiar with the process. So there we have, like I said, our surface springs are created within a couple of seconds thanks to that option. So now let's move on to creating our response spectrum, or excuse me, our loading, our seismic loading. So go to loads boundaries here. And then what we'll do is first let's create our ground acceleration loads. Okay. So as you can see, this drop-down menu, or excuse me, this input window comes up. So the first thing that we need to do is we don't have any sort of loads created or defined. Everything's blank. So first, click on this icon here, and let's create our first mode. So first, let's create a long period wave. So what we'll do is we'll have a long period and a short period wave. So there's sort of two. We want to run the analysis for two types of earthquakes. One's a long period, one's a short period, and we'll get them from the database, and I'll show you that in a minute. But first, let's define this one. So a long period wave, and what we're doing is we're defining just sort of a load set. So the properties obviously haven't been defined yet, but we're just naming sort of this blank set, and then later we'll assign the properties to it. So what we want to do is we'll make it linear. The analysis method will be direct integration for now. So as you can see, the properties change when you go from one to the other. So direct integration, just to keep things simpler here. End time, this is very important. So 20 seconds. That's the length of the length of the earthquake or the wave. Time increment, let's leave it at 0.01. So that's fine. Number of increment steps for the output, let's leave that at 1. And then modal damping. So here we'll input manually. So for the frequency, let's make it 1.7897, and I'm getting these values from the tutorial that was provided. Obviously, I gave you all a copy of this, so you can look into it a little further, afterwards. But these are just sort of the default values assigned by the tutorial. Obviously, depending on the wave you're using, these modes will differ. And the second sort of default value that was given is 3424. And then the damping ratio, these are the same for both modes. It's 0.05. So keep in mind, the damping ratio is relatively low. So then, because of that, we should get a sort of high level of oscillation during our results. So here we have everything sort of set up. So let's add it. So here's our first case. So once again, this is still, technically a blank case since we don't have an acceleration assigned to it, but we'll change that in a second. And then we'll also create a second case for the short period wave. And then everything here will stay the same. So, all of these sort of parameters here are same for both waves as far as mode length, the analysis method, etc. It's really when we define the acceleration itself that these two will be different. So what we can do is we can just add this one. So now we have these two titles, or these two parameters, upon which we'll assign specific load accelerations in just a second. So here, ready? So now, as you can see, our drop-down menu, we have two to choose from. So now, let's define our accelerations. So first, let's check on acceleration in the x direction, and then we don't have any functions available yet, but we'll select those functions. So just go here, click on this tab. So as you can see, there's sort of a pattern here with these input menus. When I started, there was nothing in each of these, but if I wanted to find a sort of set or a function, just click on this tab and you can create a new one. So here I don't have any functions yet. I'll click on this tab to define two for my drop-down menu. So click here. Okay, so now this is very key. So as I said previously, you can get your time history graphs, from a database, from some public source, and typically they come in a spreadsheet format. So you'll have your graph, but then you'll also have, your spreadsheet X versus Y, and you can import it directly from an Excel spreadsheet using this option here. This allows you to go through your computer, select the Excel spreadsheet you want, or also what you can do is you can even just go to your Excel spreadsheet and copy and paste it directly into here, just using just copy and paste. So Control P, and then click Control V in here, and then everything should line up accordingly. But as I said, another great sort of function or feature about the program or SOILWORKS in general is that time history functions are loaded into the program itself. So that way, you can just skip that step. So if you click on this option here, and as you can see, here's the database. And if I click on this drop-down menu, here I have all these different earthquakes that are available to me. So these are, some of the most prevalent time history graphs that are used just in the industry. A lot of these are, for the South. I know these are used in Asia. Some of these in the bottom. But there's many that are used here in, America, particularly the West Coast. But just for this particular tutorial, I think it was done out in Asia. I think either in Korea or Japan. So these two time history graphs are used. So just to to stay consistent with the tutorial, we'll use these. But I think San Fernando, Hollywood, obviously those are for the West Coast, Mexico City if you're working in Latin America. So once again, a whole array of time history graphs are available to you. So let's select the first one here, the Tokachi, and then you can change the amplitude and the time scale. But we'll leave those for the default values for now. Click OK. Now, as you can see, a very detailed, in-depth time history graph is there for you. So that'll be our first function, so we'll add it. So, it's here to choose from. And just keep in mind that if you have, for whatever reason, if you want to run an analysis for multiple, earthquake types or time history graphs, you can create as many as you want over here. But just for this particular tutorial, we just had two. So what we'll do is we'll go here again, and we'll select the other Japanese one, the Miyagi. Click OK. And then we'll add it. So as you can see, now I have two time history graphs to choose from, both of which have slightly different characteristics. So these are my two. These are the two time history functions that I'll be using for my time history analysis. So what I'll do is I'll close here. Okay. So now I have these two functions to choose from. Okay. So now what I'll do is I'll assign these to my waves. So for the long period wave, let's assign, let me just double check here. Okay, so we'll assign this to the Tokachi wave. Make sure this is checked on and click add. So now here I have my acceleration load. Now, you'll see, I'm sure some of you have noticed here, previously both of these were in blue, this 1968 Tokachi wave and then long period wave. That means none of them were being sort of used in the model, or these weren't created. So as you can see, these bottom two here, 1978, so this function, and then the short period wave, these are in blue, meaning that the short period wave currently doesn't have a load function assigned to it. So that means you have this this set defined, but it's still sort of blank. Until you assign it a particular function or particular load, it's not going to be in use. So here, what we'll do is we'll change it to short period wave. We'll change this to 1978, the Miyagi. Then we'll add it. So just keep your eyes on this as I add it. So now they're in blue, or excuse me, now they're in black, which means now they're both. So now this short period wave has been assigned a function. So that way, you'll be able to assign it when you're creating your analysis case. Okay, so it's really important. So whenever you're doing any sort of project, this is very key, to make sure that all of your make sure that all of your sort of material properties and all of your loadings, make sure they're all in black. If one of them is in blue, that means one of them is currently not in use. You need to go back and you need to see how to assign it. The only thing that can be in blue is the base here, which is just sort of a default mesh set, which if it isn't actively in use, it's all right, as long as the ones below it are. So that's another important thing to check for. If you have maybe a model that's giving you some issues, it's always a good rule of thumb to go back and check over all of your sort of properties, or excuse me, all of your elements, just to make sure that all of them are assigned, because that's where a lot of sort of maybe sort of failed analyses or maybe sort of errors come up, is that you have something assigned but it's not actively in use. Okay. So now that I have my time history functions created, as well as my surface springs, I can create my analysis cases. So in order to do that, let's go to Analysis. Now let's go to Analysis Case. So as you can see, I don't have anything created yet. And another thing of note, as you can see, I'm going from left to right. So I started off by creating my geometry, and I created, oops, let me close this. So I started off by creating my geometry, doing my drawing, importing my CAD file. Then I created my structural properties, I did my meshing and my surfacing. And then I created, then I did my surface springs, and then I did my loads, and now I'm ready for my analysis. So, just as far as the workflow goes, it's from left to right with these icons here. So that's just another thing that SolidWorks does in order to sort of streamline things for engineers, to make things easier to sort of understand. Because, finite element modeling is sort of a lengthy process, but if everything's sort of ordered this way, it's a lot easier to not miss a step. Okay, anyway, so going back to the analysis case, so now, I'm moving from left to right here. I can create my analysis case. I don't have anything created yet, but if I go to add, let's create my first analysis case. So first thing you want to do is make sure you have the right analysis method. So this is a very sort of simple error to make. This is something I sort of forgot when I first started using the program, but now, this is one of the first things I always do when creating my analysis case, is I check the analysis method. So if I go to this drop-down menu here, you have to make sure that your analysis method is lined up with the type of analysis you're running. Obviously, if you don't do so, the analysis won't run, and you have to go back and change it. So, this is a time history analysis. So go down here to time history analysis, make sure that's selected, and then after that's selected, you can type in the name. So let's name this time history analysis, and let's name it the long wave in parentheses. So we'll use the long wave function. All right. So here, what you can do is, we're using all of the mesh sets. Since this isn't a construction stage analysis, everything will be present. There's only sort of one model, or there's only sort of one case really, as far as your seismic for this particular wave. So what you can do, instead of having to drag and drop them, individually, which you could, but it would take longer, you can just click on this tab here, use all mesh sets, and everything will be transferred automatically. Same with boundary sets. You only have one boundary set, but you can just use that, and then everything will be transferred. So what you don't want to do is transfer all of your load sets. You only want one load set per analysis case. So this is our long wave function, or our long wave case. So just select long period wave and then drag and drop it. And as you can see, that's our first case. And just click apply. And now we have, if you go to move this over here, we have our first analysis case for the long wave. And then naturally, we're going to have a second case for our short wave. Okay. And the only difference is going to be, instead of the long wave function, what you can do is you can just drag and drop this over to the left and bring this over to the right, short period wave, and then click apply. And now we have, an analysis case for the long wave as well as the short wave. Okay. So now at this point, what you would do is you'd go to analysis, and then you would make sure these two are checked on, and you'd click here, perform analysis. Now, because this is a time history analysis, the analysis itself doesn't take very long to run. It's about maybe 3 to 5 minutes tops, depending on the speed of your computer. But just in the interest of time, I actually have a completed model just so we can go right to the results. And some of you are probably wondering when we're going to do the response spectrum analysis. We'll do that in a minute. But first, I just want to go over the time history analysis results, because there's something sort of unique about the results that I want to go over. And the modeling of the response spectrum analysis is actually very simple and very straightforward. Since we've already done most of the modeling, it's mostly just creating the load function or response spectrum, which takes literally like under a minute. So first, let's go to just the results, and then we'll go back and do response spectrum. Okay, so once the analysis is complete, your model should look something like this. As you can see, I have all of my results listed here to the left. So here, for time history analysis long period wave, I have these sort of sets of values here. So for eigenvalue analysis, that sort of goes back to the different modes. I won't get too deep into it, but eigenvalue analysis is something that's sort of done automatically when you do response spectrum or a time history analysis, because it gets the various modes for the earthquake. That's something you don't really need to worry about if you're just focused on displacements and strains, etc. Okay, so here, as you can see, under time history analysis, long period wave, you have your time history maximum, your critical values for maximum, minimum, and then also for sort of an all-encompassing one. And you have that for each of your cases here. So before I get into just the sort of the structural or the responses for the ground elements, first let's take a look at how to draw some graphs, because I know when whoops, sorry about that. Okay. Okay. Sorry, I have the two screens here, and I'm trying to make an adjustment on my other screen using the cursor. It's not really working out. Okay. So just a second here. Okay, so first let's take a look at some results graphs. Let's generate some results graphs. So first, go to results. And once you're in post-processing, once the analysis has been run, this tab becomes particularly important for extracting your results and showing certain displays. So as you can see, something very unique about the dynamic module is this tab here under the results section. So this is how you get certain results graphs for your seismic analysis. So let's go to result graph here. Okay. Or actually, sorry about that. I'm getting a little bit ahead of myself. So we'll get back to this later. And so, basically what I'm going to do here is I'm going to get sort of a results graph for vertical displacement for each of my waves. But before I do that, I actually need to define a certain point of study. So sorry about that. I just need to take a step back, and we'll go back to this in just a second. All right, so first go to loads boundaries analysis. Now, as you can see, all of these are grayed out except for this tab here. So this tab is very important for defining your time history results function. So let's click on it. And what we need to do is we need to define sort of a point upon which of study. So typically, since this is a bridge abutment, I'd want the vertical displacement at this top point here. So let's select it. Okay, as you can see, it's selected now. It's one node selected. And then also, let's make sure, okay, so it's the displacement here, perfect. And you can change these according to your needs. So let's leave this for the long period. Displacement's good for now. And then let's set this to the DZ direction. So I want the displacement in the vertical direction, not the horizontal direction. Okay, so we'll add it. And then we'll do the same thing. So, the node will stay the same. These settings will stay the same. The only difference is I'll change the analysis case. So instead of the long period, I'll have one also for the short period wave. So click Add. So now I have two functions, I believe. Let me see. Okay, so it should be set. Okay. So let's go back. So now that that's defined, just go to results, go to draw result graph. Okay, so I have it for the first one, but not for the second one. Let me go back and make that change. Let's go back, change this to DZ, make this a short period wave. We'll select this node. There we go. Okay, so now we have two sets here. And I should probably rename these to make this a little more clear. So this will be long period. So we'll modify it. Okay, I'm having a little trouble changing the name here, but just for now, we can just differentiate. This top one's a long, this bottom one's a short. So we can close, we can go back to results, go to our result graph here. Okay, so now we have both waves. So what we can do, let's say for example, I just want to draw the result graph for my first wave. Just select this top one here, and then make sure these are all set to what you want. These are just ways to sort of alter your graph. So what you can do is you can draw it. And as you can see, here's my displacement. So for the vertical displacement, for that top node here, this is what it looks like here. And I believe the units here are in feet. So as you can see, depending on where you're at with the earthquake, it jumps up 0.0001 feet or goes below. And let's say we want to see how that sort of compares to our second earthquake type, or our second time history function. What we can do is we can check this bottom one on, which I believe corresponds to the short period wave. Click Draw. Next, as you can see, we have a direct comparison here. So this is something that's very key, and you can do this for the displacement for any point along your abutment or your foundation, etc. And you can export these graphs to to a Word document. You can export it to an image file. So when you're doing your final report, I know a lot of engineers, they like to have these sort of graphs sort of presented very clearly to the client. So that's another thing you could do. So this is something very useful when you're extracting your results. So instead of having to put certain results in an Excel spreadsheet, creating the graphs yourself, you can just very quickly create multiple graphs for for multiple points, etc. So once again, something very useful for your result extraction and when you're creating your final report as well. Something that could save you a great deal of time and a great deal of hassle. Okay, so that's how you draw your results graphs. And it's happening again. Sorry about that. Okay, so now we'll move on to just looking at the let's say you want to take a look at the displacements just directly on, via a contour diagram. So let's zoom in here, and let's take a look at, our first analysis case for the long period wave. Let's take a look at our vertical displacements along the entire along the entire model. So here's our vertical displacement. And keep in mind this is a maximum value. So as you can see, the maximum vertical displacement occurs at this sort of top left corner here, and our legend is over here. So the units are in feet. And then let's say, for example, also, let's say I want to get maybe my values for a certain range here. So if you go to result, and if you go to probe result here, and actually I did that a little fast, let me do it again. So go to result, and then under detailed results, this tab here, select this option. It sort of looks like a piece of paper with a tab or a highlighter on it. Just click on it, and then what you can do is you click on maximum. You get your maximum value and sort of exactly where in the contour diagram is. And as far as your minimum values, technically, all of this here is 0. But what will happen is it'll take sort of, the bottommost point, and it'll give you your minimum value. But just keep in mind that everything in deep blue is technically 0. So there's no sort of vertical displacement along these areas. And then let's say I want to get maybe a list of values for this green range here. So what I can do is I can just tag these nodes. And here I have a spreadsheet developing, which tells me, what exactly, the exact locations of the point as well as the values. So if you're creating a spreadsheet for your final report or for your submission to your client, this is something that's useful. Typically, what I've seen a lot of our clients do, or a lot of engineers in general do, is they'll have something where they'll have maybe a range of values tagged, and then I'll also have like a spreadsheet sort of next to it. Maybe I'll take a screenshot, something like this. So that way the client can get a better understanding of what's going on. They can say, okay, this sort of value here from X to Z or whatever, it has, a value ranging from, this value to that value. That's a maximum, that's a minimum, etc. So that's another way that you could do your graphing, or extract your results. Another great sort of option that's available to you is to use the the on-curve diagram function. So this was something that was sort of asked to me a couple of weeks ago by a client who wanted to see if SolidWorks can create graphs directly. So the program itself can't create or export, like specific graphs directly to Excel. But what it can do is it can create the graphs through an on-curve diagram. So let's say, for example, I want to get the displacement or the vertical displacement represented via a graph, or via sort of a curve. So what I can do is I can just select this one point here, and as you can see, as I stretch the 2 points out, I can get the maximum and then my minimum for this sort of curved diagram here. And if I click, this can be saved for future reference. So if I click OK, it'll be saved, and I can turn it on and off, and I can create as many of these as I need. So this is another thing that's very useful to sort of give a better visual representation of what's going on with your model. Okay, but now just to go back to the results that are available to you. So those are the two main sort of useful functions for extracting your results. I won't go into too much detail about the other ones because they're not as used as much. But if you have any questions about them, we can talk later. These sort of options here just change the display settings. They don't really help you extract results. They just help you sort of change the display settings of your model. So we won't talk about those for now. But here, once again, going back to the results that are available to you: horizontal displacement, vertical displacement, total displacement, and then ground element stresses. So you have your total stress. So as you can see, stress is occurring, sort of higher around the area, around the abutment, naturally. Total stressing, principal stresses. And then also, since we're analyzing the foundation of an abutment, it's very important to understand what's going on with each of these piles here. So in order to view that, just go to Beam Element Forces. So click on this tab here, and then you'll be able to, and let me zoom in here for you, you'll be able to get your axial forces, your shear forces, and as well as your moments for each of your piles. So something also that is very useful. Typically engineers will take a screenshot of this, and they'll have maybe like some sort of spreadsheet with the maximum and the minimum values. They'll have that in their final report. And just keep in mind that all of these results are available to you for each of your analysis cases. So within each of these cases, you have two main cases, but then within that, you have like a total of 3. You have your maximum, your minimum, and your all. So, once again, a great range of results are available to you. So before I move on to the response spectrum, I just want to go over one sort of very special and unique analysis capability, which is the animation feature, which is something that's very unique to the dynamic module. So because seismic analysis is so, based on, is so reliant, I guess, on time, within a couple of seconds the loading changes very quickly. It becomes very important sometimes to see how that loading changes or to see how the results change over, a few given seconds of the earthquake. So in order to provide for that need, SoilWorks has a very specific animation function to help with that. So let's go to first. Let's select what we want to look into. So let's go back to displacement. Let's go to vertical displacement. So we'll go with this for now. And then what we want to do is we want to see how the vertical displacement changes over time or over the length of the earthquake. So I believe we specified a total of 20 seconds, in the input parameters. So this will be how the displacement changes over like 20-second increments of the earthquake. So first, let's go to record animation. So go to results, and then our detailed results here. So these are very specific towards the dynamic module. Click on this icon here. This is the record animation feature. Just click on it. And when you do so, it goes away at the top screen. But here, as you can see, there's a function here called record. So just click on this this icon. Okay. And then it'll record the displacement change over 20 seconds. And what you can do is you can press play here. Okay. So look how it goes sort of back and forth. And this is, from the very beginning to sort of the end of the earthquake. So naturally, the part that was shown, or the part that we showed initially, was the maximum. But if for whatever reason you want to see how it gets to that point, or how the model changes up to that point, just click play here, and you can see very slowly how the model changes, or how the sort of the contour diagram shifts along each point of the earthquake here. Okay, and you can do that with any of your. So let's do it for total displacement this time. So we'll hit record, click play, and then we have the same sort of option here. So what you can do is you can freeze it, and then you can get your results for, it's sort of hard to extrapolate where exactly. I think this would be around like maybe 18 or 15 seconds. But in any case, you can just get your results again just using the same process. So that's another thing that could be, particularly useful for you. And then, for those of you who want to draw your time history, so for example, let's say you want to see how the results change specifically along, which point of the earthquake, or along the time history function. Go to results, and then go to draw hysteresis. Go to this function here, and then just make sure to select your time history function. So let's select our first set, and let's select not the axial force, but let's see, select the displacement again, vertical displacement. And just use your mouse cursor here to move this just along the length of the earthquake. And it takes a few seconds for the program to sort of, and this is important too, make sure to click apply immediately. That way you can see immediately what's going on. So just move the cursor along the length of the function. And once again, it takes a couple seconds for the program to catch up, but you can see maybe during this sort of peak point, you'd want to see what your maximum, or what your vertical displacement looks like. Just move it along, and as you can see, it changes very rapidly. So just keep in mind that with time history records, it's showing how the load is changing very quickly. So it goes from positive to negative within, milliseconds or split seconds. So that's why there's such a drastic change in displacement, because the loads are shifting so fast. But just using this function, you can really get a clear picture of what's going on, or anyway, a much clearer picture. It's not exact, but it's a much clearer sort of simulation of what's going on with your model along the length of the earthquake. And once again, it's just a matter of moving your the cursor over. So once again, if you want something very detailed and very sort of clear, you can use these options to get that better understanding. Okay. So I know I'm going over this pretty fast, but don't worry about it. I'm going to post the recording up tomorrow. I'll send you all the link through an email. And then for those of you who didn't receive a copy of the tutorial, I'll make sure to send you a copy. That way you can try this project for yourselves. So before we wrap up, we still have to do our response spectrum analysis, and don't worry, it'll take just under a minute. So let's take care of that real quick, and then we'll wrap up. So going back to my unfinished model, or my unanalyzed model anyway. So now we have my I have my time history analysis. Now I just want to create my response spectrum analysis. So, let's say, for example, you're working on maybe a smaller scale conventional type project. You don't need time history analysis. Well, the process is actually even simpler. So just go to response spectrum, click on functions, and then, for those of you who are familiar with response spectrum functions, they're much more straightforward. They're much more simple than time history functions. You can import them, from your own database, from your own Excel sheet, but also you can select them from our database. So let's go with this one. And then here you have your different site classes. So, once again, depending on the site class you're in, let's say you're in site class C. Click OK. And, there's your response spectrum function. So just click Add, and it's there for you. And then now just go to Load Set, and we'll just name this response spectrum load. We'll just assign it the function, so it'll be in the X direction. And then we'll just select the function we defined. And keep in mind you can define as many functions as you need. If you want to define another one, just go back here and just import a second one. Okay. So here's our function. These values are fine. Yeah, damping ratio. Okay. So click Add. There's our response spectrum load. Okay. So that's essentially it. That's all it takes to create your response spectrum load. Now all you have to do is create your analysis case. Just go to Analysis, go to Analysis Case, go to Add. And then under Analysis Method, make sure to click on Response Spectrum Analysis. I will just name this Response Spectrum Analysis. We'll use all our boundary sets, all our mesh sets, all our boundary sets. And then our only response spectrum load is the one we just defined. So I'll close, click OK. And then you would just run your analysis. Just run the analysis. So let's say, for example, you ran these two previously. You can check these two off and just click to perform your analysis. So let's run the analysis now, because the response spectrum is very fast. So we'll run the analysis now. It's running the number of iterations. Here we go. There we go. And as you can see, like under maybe like 5-6 seconds, the analysis is done. So let's go check our response spectrum results, and it's the same sort of essentially the same results that are available to you. So, here you have your beam element stresses, your axial, your shear, your moment, and then your displacements as well. So your vertical moments, or excuse me, not your moment, your vertical displacements, sorry, and your horizontal, your total displacement, your ground element stresses, they're all available to you. Just keep in mind that because it's a response spectrum analysis, those sort of other features, those time-based features that I showed you, they aren't available to you just because the analysis isn't as detailed. So for example, the draw graph function, the record animation function, they're not available to you with response spectrum analysis. But for conventional type projects, you don't really need those types of those functions anyway. Typically what you'd focus on is just the response of your support structures as well as your vertical displacements. So this is all you really need for response spectrum analysis. And as I just showed you, it's very simple, very straightforward. If you're familiar with the response spectrum analysis, you should be able to start using the program immediately to start doing your analysis. In any case, and then also your eigenvalue analysis. Let's view this really quickly before we wrap up. So as you can see, I created up to 30 modes for you. So these can be defined as well. So for example, if you want to run a shorter analysis or you want to run more modes, you can define this in the let me go back here. So let's say go to analysis case. Let's go here, go to modify, then go to analysis control data. So using this function, you can sort of set certain parameters for your analysis. So here, my number of frequencies was 30. If I want to turn it up to 50 or 60 for whatever reason, I can just turn it up and I can have, more modes. Or if I want to run a faster analysis, I can cut this down. Same with the number of iterations. The number of iterations sort of controls how sort of detailed or how in-depth your analysis will run. But these are just the default values, so they're not too slow, but they're not too fast. Typically, when you submit your final report or when you do your final analysis, you might want to turn these up a little bit just to ensure a higher level of detail, or of accuracy anyway. In any case, I think that about concludes it for our lecture today. I hope you all found this useful. Just keep in mind that, even though I went over some things a little quickly, I will be posting a recording on. Let me just put up the last slide of the show here. Yep, thanks again for your attendance. So the recording will be available tomorrow. I'll email everyone who attended, get a copy of the link as well as the tutorial. We'll have another session which will take place tentatively in March. I don't have a date or a topic quite yet, but I'll do some surveying. We'll ask around. It'll most likely be either a seepage or a foundation project. I'm not sure. I still have to do a few more follow-up calls, but as soon as the data is set, I'll send you all the link. And if you have any questions at all, feel free to contact me. Here's my number and my email address. So once again, thank you all for your time and your attention. I really appreciate the feedback that you guys keep giving me. For those of you who are new to the program, I'll keep following up with you to help you get along with the software. And for those of you who need particular assistance, once again, my door is always open. Feel free to contact me. All right. Well, thank you again for your attendance, and I hope you all have an excellent day.